Dream to become the next Sir Isaac Newton or Albert Einstein? Learn from the master. Refath Bari. Watch his videos to achieve your dreams.
Hello folks, so welcome to the 9th lecture in linear algebra. Today, as you can see, we're talking about vectors and linear equations. Last lecture I talked about linear combinations. Today we go deeper into that. So go ahead and get started with the do now. Do now today has two parts. Both of them are exercises. So part 1, try solving this. I'll give you a vector, let's say 1, 2, and let's give you two vectors this time.
Can you solve it together?
Yeah. 3, 1, let's say 1, 0. Let's see what happens. Good luck, and I'll give you some time. Oh, seems like one of our students already has some answers.
So I can figure this out on the go. So A is 2, 4.
A is 2, 4.
B is negative 2, 6 plus 3, 0. So that's gonna be just regular addition. So 1 and 6.
1 and 6. So let's see how he got that. So for part A, all he did was scalar vector multiplication, right? We covered this last lecture. So last lecture we covered scalar vector multiplication. In this do-down we see it in action. And last lecture we also covered linear combinations. So here I have a linear combination of two vectors, and that gives me 1, 6. Okay, so I have a linear combination of one vector, I have a linear combination of two vectors. Now let's move on to the lesson where we see what linear combinations actually do for us.
Like the way it teaches instructor.
Thank you. So we begin with the simpler example, right? What if we just have one vector? Okay, so let's say I have a vector, the same vector I did last time, and I multiply it by a scalar 2, and I got 2, 4, right? All I had to do was multiply 2 by both of the components of the vector, get 2, 4. But let's see how that looks like on the plane. Okay, so we have, let's put all the tick marks. 1, 2, 3, 4. So I have the vector 1, 2. I'll draw it in green right here. And when I multiply it by the scalar, what am I really doing? When I multiply it by 2, I'm essentially doubling the size of my original vector. So let's call my original vector v, and let's call this scalar, I don't know, we'll call it c for constant. So when I multiply my vector v by c,
it gets c times larger.
it gets c times larger. In fact,
Or the inverse of c times smaller.
right there. So you can see this is
This
cv
CV, yeah.
compared to my original vector, which is this green v.
But you could also scale down v, right? Because if you multiply a normal scale by a scale,
C can be negative.
yeah.
So
But you can scale down v by multiplying this vector by a scalar that's less than 1, like 0.25. That
So
would make it 4 times
my
smaller.
exactly right. So my constant doesn't have to be 2. It could, for example, be negative 2. Negative 2 would take my original vector v to where? It would take it all the way down here, right? So let's call that negative 2v. If my scalar is 0, what does my
That would
vector
give us
become?
the 0 vector.
It would give
But this
me,
one is very important.
right. So if I have my scalar as 0, my vector v would go to the origin, right? And of course this doesn't have to be a whole number. I could even have rational numbers as my constant. it doesn't matter. The point is, you see that all the combinations of my vector v are on this geometric object. And what is this geometric object? It's a line.
Vector, yeah.
It's a line, yeah. So you can see all the linear combinations of this vector v lie on this line to the origin. So what can we say? Well, we can say, let's write it in blue. So I will say all linear combinations of my vector v, or CV, because I'm multiplying it by a scalar, lie on a line.
I have something I would like to say. So,
Yes.
You've used this graph in past lessons. The line of the vector, these vectors lie in, the line, you know what I mean.
Yeah.
It must be, if you were to label V as the matrix AB, the vector AB, then the line would be y equal bx over a.
That's a very good idea. So what he's saying is that instead of having a vector with components 1, 2, we can have a two-dimensional vector with components a, b. So we can generalize this so that we can have any component a, b.
So then the line that these vectors would be stuck on
Will
is
have
y
the slope.
equal b over
Yeah.
ax.
Good. So the same concept applies to any two-dimensional vector or any n-dimensional vector. So we say all linear combinations of CV lie on a line. So now we move on to the next step. Instead of having a linear combination of one vector, I'm going to try to deal with two. So having two vectors is definitely not as easy as having one. But let's see if we can try to understand what the linear combinations do for us. So now I'll have two vectors, let's say 1, 2. Again, I used 1, 2 in the last example too. And maybe, I don't know, -1, 3. Okay, so let's make it different. -2, 3. So, and we'll have some constants, CV. Okay, let's call this W, let's call this X. Okay, so I have two vectors and I have two scalars multiplying both of my vectors. Now these two scalars can be anything. Let's start off with actual numbers instead of variables. So
2 and 6?
2 and 6, let's say. So 2 and 6, I want to choose smaller numbers. Let's say, let's go with 1. So 2 times this vector gives me 2, 4.
2, 4. And
1 times this?
-2 and 3.
3. And what is this if you add these up?
2,
0, 7.
0, 7.
Yeah,
zero,
that's
7.
exactly right. Now, what does this mean on the plane? Well, let's go to the plane.
Yes, I will work together. Thank you.
Just like we analyzed one linear combination on the plane, let's analyze two linear combinations on the plane. So let's see how that will look like. 1, 2, 3. Okay, our first vector is 1, 2.
Are you going to analyze the vector 0, 7 or our answer
Yeah.
vector?
Okay, so that's my W vector. Let's call that
And then
W.
-2, 3 would be facing backwards.
-2, 3 would be facing backwards.
Yeah, and then a bit taller.
So this is, let's call this vector X, right? And my resultant vector is 0, 7. So let's see where 0, 7 is. 0, 7 is 1, 2, 3, 4, 5, 6. Wow, I got lucky.
Just a straight line.
Now, with a combination of two of the green vector and one of the blue vector, I was able to get this red vector.
Because
Now,
X and W are perpendicular.
they are not.
They seem
They may
perpendicular.
look perpendicular, but in the future we'll look at a tool called dot products that will let us see if two vectors are perpendicular. But these are not perpendicular.
But it looks like the red vector 0, 7 is in the middle of x and w.
But you cannot see.
The resultant.
Yeah. So now let's try a different combination. We tried a combination of 2 of the green and 1 of the blue. Now let's say I don't know. Let's try -1 and 2 of this. Make things a little interesting. So what is this?
-1, 2.
-1, 2.
And
minus 4,
-4, 6.
-4, 6.
They're both facing backward.
And
minus 5, 8.
-5. Okay. I hope I have space to draw it. So let's see. -5, 8 is what? Where?
You didn't draw
1,
enough
2, 3,
tick
4,
marks
5,
on the
6.
y-axis.
Oh, 1, 2, 3, 4, 5, 6, 7. He's right. So let's add one more tick mark on the y. So, okay. So we go to -5, 8, right? So 1, 2, 3, 4, 5, all the way to here. So my resultant vector is something like this.
Yeah.
Okay, so I got another red vector using another linear combination of these two vectors. Now I'm not gonna belabor the process, but if you keep doing this for a few hours, you'll realize that you can get any vector you want, not just these two, but any vector in 2 dimensions. You
If
can
you-
get it, yeah,
Yeah.
from only these 2 vectors. You
If
can
you're
get any
pointing
vector.
in opposite directions, then yes, you can.
Not opposite. In fact, it doesn't have to be these 2 vectors. We can generalize it, just like our student said, for any vectors, A,
So
B,
A, B, and C, D.
and C, D.
Come on, 3D.
So any vector, any 2 vectors in 2D, their linear combinations are the entire plane. So how can we say this in a sentence? We can say all linear combinations of, let's call this scalar C, we call this W, let's call this D, and I call this vector X, is a plane. Okay, because what is this plane? This is the plane R2. So even if this is confusing, next lecture we'll go into it more. Now let's go on to a easy exit slip.
Of course, it's easy.
Yeah,
Everything's easy for me.
yeah, because
I know linear algebra seems the most innovative out of all the
Yeah.
math concepts.
identify. I'll just okay.
Linear combinations.
I don't know, 2, 6. So these are your choices. Good luck. So the answer is one of these 3, or maybe more than one. Good luck.
I got it.
It's a lie. But it's okay. Okay. Thank you for watching.
Science Lab to fall in love with math and science, especially programming.